This is lecture 12. It's the second lecture on chapter 5 about the second law of thermodynamics. What we will do here is we will explain the effects of commonly encountered irreversibilities. Then we will make the difference between internal and external irreversibilities. We will then describe processes that have no internal reversibilities, that are internally completely reversible, and we will use that to derive the implications of the second law on these principles in power and refrigeration cycles, and we will then get to a hint of what the Carnot cycles will be, which will indeed be described in detail in the next lecture. So let's go back to classic friction and look at friction as an irreversible process. So if you have a solid block that's sliding down a slope like this from an initial state to a final state, the internal energy between the final state and the initial state, plus the difference in potential energy, plus the difference in kinetic energy, which is, let's say 0, is the heat minus the work. So since this is 0, and let's assume for a minute that the process has no heat exchange at all, and let's do no work. So you notice nothing here has a cylinder or a shaft that does work on the block. Well, then the change in internal energy reflects the change in potential energy. In other words, just a change in height times the mass of the block and the gravitational constant. So this friction process, the block going down the slope, is irreversible. This motion you cannot do unless you apply work to your problem, which by definition we said we weren't doing. So if it were possible to do this without applying work, then you would have the internal energy also return from U final to U initial. Well, let's take a look. Can we make this process happen? On the one hand, yes, you can make the process happen, go from initial to final, final to initial, if you have a little pulley that lifts the block and does work on it. If you do that, the work you do on it will be the difference in potential energy. So that is feasible. But now what you cannot do is get the same effect by applying heat to the problem. If you just apply heat here, that won't make the block go up. This is very intuitive. So you can see that there is a difference between heat, which can't do it, and work, which can. Yet, from first principle, heat equals work. So why? If D, let me now relate this intuitively obvious statement to the second law. So if D could be done, the system could have done work only from a single source of heat, Q. Namely, I could have taken the system here, put heat into it, made somehow the block go up magically, and then take that block with my pulley and bring it back down, which would then have given me work on my pulley. So I would have been able to take heat from a single source and get work done at the end of the day. That would have violated the Kelvin formulator of the second principle, as we saw it in the previous lesson. I can do this with a more probabilistic, more microscopic idea. And this is something that is not exactly in the class, but I think helps with the understanding of things like you can't do this. What does that exactly mean? Well, it's a probabilistic argument, which you'll see in a statistical thermodynamic. It's a statistical fact. So let's simply take a volume here that consists of a gas that's all on one side of a partition that I have put in my volume, and the other side I have vacuum. Now, I release that in an irreversible process to have my gas diluted over the whole volume. So you can't go back unless you do work. What does that mean exactly? It has a statistical meaning. So what you're really asking is, what are the chances to have all these Na particles starting from this situation suddenly all come up on the right-hand side of the partition? So what would the probability be that this transition from here to here happening totally by chance? Well, the probability that an individual particle be on the left or on the right is 1/2. Well, the probability that an individual particle be on the left-hand side of this is 1/2. If you have two particles, probability that they both be on the left is 1/2 to the power 2. If you have 100 particles, probability is 1/2 to the power 100. That is 10 to the power minus 30. Now, bear in mind, you don't have 100 particles. You have 10 to the power 23 particles. But let's just consider that you only had 100 particles. If you were to take a measurement of your particles left and right every second, you would have, to get this probability to happen, to wait 10 to the power 30 seconds. What is 10 to the power 30 seconds? 1 year is 10 to the power 7 seconds. So that would mean you would have to wait 10 to the power 22 years. Well, the age of the universe is 10 to the power 12 years. So that is the statistical meaning. This doesn't happen. It cannot happen within the age of the universe that even 100 particles end up here. So that means that is the meaning of the word never. All right. So let's go back to the reversible process. The reversible process is one where you can start from an initial state, go to a final state, and then just come from the final state and go exactly back to the initial state. That is a reversible process. It can take the same path from initial to final state and then back from final to initial state. So let's bear in mind this is an ideal situation. No process is truly reversible, and we can approach reversibility by minimizing the irreversibilities. In the previous example of the block on the slide, that just means greasing the slide, which decreases the friction, and that decreases the irreversibilities. So now let's take an example, a series of examples of things where we minimize the irreversibilities. The most intuitive example is the pendulum, where I can take this, minimize the friction of this hinge, minimize the friction of air, take the pendulum up on one side, let it go. It swings and it swings back and it comes almost to the same point where it was to begin with. So the potential energy that you had in it at the initial state is almost entirely recovered. The internal energy of the system, therefore, between the initial state and the final total state, so back and forth, is the same. That is an almost reversible cycle. Now let's take a look at why we needed the concept of quasi-equilibrium, which I introduced in lecture 3 or 4. Well, take your ideal gas with an equation of state that's PV is nRT, and take your piston and push on this ideal gas. Well, if you push really fast, you're going to have a change in pressure and a change in temperature that accompany each other. In other words, if, for example, you push really fast, you'll have a dP dV, a d of PV dt, which is an R bar, number of moles is constant, and the gas constant is constant, so that is dr dt. So if you push really fast, you're going to have a high dr dt. Well, that dr dt must be positive. So in other words, you're going to heat this gas, and since you will have losses, that heat will dissipate outside to the outside air. So a high dt means that the heat transfer to the outside is high, means that the system is irreversible, because the heat you have lost to the outside you cannot get back. That was the second principle. That is what we say is a system that evolves outside thermodynamic equilibrium, quasi-equilibrium. So now to revisit this quasi-equilibrium we defined when we looked only at work, we have to state here that what we do is push on this gas very slowly. If you push very slowly, this time derivative is small. Therefore, the time derivative of T is small. So dt dt, the temperature d time, is small, which means that the heat exchange to the outside is small. There's no heat transfer to the outside ideally. That means that the process is almost reversible. That is a means to minimize irreversibilities. And that is what happens when we say that the system evolves in quasi-equilibrium, thermodynamically in quasi-equilibrium. So we have to consider systems in which there are no irreversibility inside the system. Now, irreversibilities are tolerated at the system boundary. You can have heat transfer that is irreversible. That we will consider. We can have the internal variables. We will assume that the system is uniform, of course, so the internal variables are the same everywhere. And then the system is going to be reversible, internally reversible. Now, from now on, these are the only cycles we will study, internally reversible cycles, and we will consider the exchanges with heat with heat reservoirs. It is a very imperfect picture, and we will show you what happens when we have cycles that are not quite like that, and we will take other approximations in future chapters. But for the moment, in chapter 5, we will only study internally reversible cycles. So let's take a look at these cycles, and let's revisit the Planck formulation for the second principle. So the Planck formulation tells you that the work of a cycle with a single heat reservoir cannot be positive. So you can, if you want, unroll this mass and let it come down and make that system do work on your system, which will then create heat. That is permitted. This was actually the Watt experiment. But the reverse is not true. You cannot take heat from just this reservoir to do work on this shaft to pull this mass up. So the dashed line is forbidden, the black line is allowed. All right, so let's write this now. du is 0 is Q cycle minus W cycle. Just assume that we are in a situation where we don't change the internal energy of this, which is not exactly what we're doing here, of course. Then you can have Q cycle to be W cycle, and that means you will have heat. You can do work on the system, and you will get heat out. That is when Q cycle and W cycle are both negative. You don't change the internal energy of the system in this case. Example, a little space heater, electrical space heater will do exactly that. Now, the best you can do is the isolated system with no motion and no work. If the work is 0, then the heat is 0, that's fine. But you cannot have this positive. So positive is forbidden. Let's say that we just stated that here. What are the consequences now for cycles? The consequence for cycles, you need two reservoirs. One hot reservoir, one cold reservoir. One that gives you heat in, one that gives you heat out. And the difference between the two then, heat in minus heat out, is the work of the cycle. So all power cycles have to have two reservoirs because this is forbidden. All right. There is the Carnot, Rayleigh, the way to phrase this in Carnot's term, and that is that the thermal efficiency of a power generation cycle is 1. Why? Because the work of the cycle is the hot side minus the cold side heat exchange. Since the efficiency is W cycle over Q hot, it's 1 minus Q cold over Q hot. Well, that has to be smaller than 1. You reject less heat than you put in. Now, internally irreversible cycles have the highest possible efficiency of all cycles operating between the same two thermal reservoirs. For the moment, this is a statement. That statement will come back. I will prove it in the next few graphs, but that is important because it also implies immediately that all internally reversible power cycles, so the reversible power cycles have the highest possible efficiency. There's only one such highest possible efficiency. So that means that all internal reversible power cycles operating between the same thermal reservoirs must have the same thermal efficiency, the same, which is the highest one possible. But of course, it's unique. All right. So let's look for the single highest possible efficiency between two thermal reservoirs. Note that this statement is independent of the type of cycle, of the fluids in the cycle, of the mechanization of cycle. This statement is general, it's thermodynamics. So I need to prove this to you. And the proof is a little long. You have to bear with me here. All right, so let's take two cycles. We take on the left cycle here, between a hot reservoir and a cold reservoir, we take one cycle that is reversible. So it takes Q hot. This is my reversible cycle. It's a power generation cycle. This is my Q cold. This is my work hot. Now I take an irreversible cycle that is internal irreversibilities. It takes Q hot. It sends Q hot into the cycle, which does work sub I, and it ejects another amount of cold heat, of heat to the cold reservoir. So QC and QC prime are not the same, because this has internal irreversibilities, whereas this does not. Now, let's take a look at this cycle and assume that they both use the same Q hot, but they don't, of course, use the same Q cold. So the work on the reversible one is the heat Q hot that we put in, minus the amount of heat they reject on the cold side. And the same on the irreversible one. This one is the same as that, but this one is Q cold prime, is not the same as that. Now I need to show you that this work necessarily is less than that work for the same amount of Q hot. That's what I have to prove. Well, here comes the proof. Let's reverse the reversible engine. So this one, instead of going from Q hot work out to Q cold, we make it a heat pumping one that takes work in the same amount WR, work in, it gets Q cold in, and it rejects Q hot on the hot reservoir. So we have flipped between the full line and the dashed line in the reversible cycle, just reversed it. Now let's take a look at the balance of heat of the combined cycle, the reversed reversible one and the original irreversible one, or one with irreversibilities. So let's dash this as the combined cycle, and let's take a look at the balance. Well, first, what is the net balance of Q hot? Well, it's Q hot on the reversible, which we have reversed, plus Q hot on this one. Well, this one is minus Q hot. This is minus Q hot, plus Q hot, which goes here. So that sum is 0. Okay, what is the net work? Well, the net work is going to be Wi, which is positive, minus WR, because we have reversed the sign of WR. Okay, turns out that because you have these equations and you have that to be 0, the difference in work is going to be QC minus QC prime. That's simple algebra here. So that would be the net work out, Wi minus WR, work out minus work in. Now, I have to prove to you that this is always negative, definite negative. Well, if it were positive, if QC minus QC prime, or Wi minus WR, were positive, then the net machine, net, would have positive work, because W net is this difference, would be positive, whereas Q net hot here would be 0, meaning we would be entirely working out of the cold reservoir only, not involve the second reservoir in the development of the work, thereby violating the second principle of thermodynamics. Here. Well, so this cannot be, this would violate this second principle. Therefore, you must have WR larger than WI. The reversible cycle in the original statement always gives you more work than the irreversible cycle. Well, the work can be equal if this one is then also reversible, of course. So that means that the thermal efficiency of the reversible cycle, which is this over QH, and the QH is not the same, must be larger than the thermal efficiency of the irreversible cycle, which is Wi over the same QH. What we demonstrated is that the reversible power generation cycle had the highest possible efficiency. We can do exactly the same for the reversible heat pumping cycles, which I show here. The proof is going to be exactly the same as for the power generation cycle. We're going to take an irreversible heat pumping cycle and a reversible heat pumping cycle, and you can walk yourself through that proof. What you will then demonstrate is that this same equation holds for the same reason, which implies now that the reversible cycle, in order to pump the same amount of heat, will take less work than the irreversible cycle, which means that the coefficient of performance, which is in cooling, which is the amount of heat pumped per amount of work, has to be larger in the irreversible cycle, because the denominator is smaller, than this is a reversible cycle. So the coefficient of performance of the reversible cycle has to be larger than the coefficient of performance of the irreversible cycle, because you divide the amount of heat pumped by a smaller amount of work in the reversible cycle. Now, what consequence does this have in terms of implying whether the efficiency is larger or smaller than 1 or this or that? Well, so for power generation cycle, the implication was that in all cases, the efficiency is smaller than 1. What is the equivalent implication in reversible heat pump cycles about the COP? Well, it's not that instructive. Let me tell you what it is. It just means that the COP has to be less than infinity. Duh. So we can do this here. We can take the COP in cooling QC over W cycle as QC over QH minus QC. All we're saying is that we cannot have a cycle where we have only one reservoir. For example, where a QH would be 0, which would be then -1, or one where we can have no QC. QC would be 0, then you'd have 0 over 0. So simply the fact that you can't have that without having a difference between the two, it's easier to explain in terms of the difference between the two. If the difference between the two were 0, that is, if the work were 0, and then beta would be infinity. And here you have the same argument. The work of the cycle cannot be 0, and then gamma cannot be infinity. But that's not terribly instructive. So let's go through the summary of everything we have learned so far in this lecture. First of all, we talk only about internally reversible cycles. All internally reversible power cycles operating between the same thermal reservoirs have the same maximum thermal efficiency. All reversible heat pumping cycles operating between two reservoirs, identical reservoirs, have the same maximum coefficient of performance. So magically, it's only the reservoirs that matter. It doesn't matter what the fluid is, air, steam, electrons. Doesn't matter what the mechanization is. All that matters is the reservoirs. So the only difference between various possible thermodynamic cycles is really the reservoir. So these reservoirs must have some mysterious characteristic theta that characterizes their heat. And that is the characterization that will uniquely determine their maximum efficiency. So we know that if we're looking at power generation cycle, the efficiency is 1 minus QC over Q hot. So for the reversible reservoirs, the internal reversible power cycles, this QC over Q hot cannot be a function of the details of the QC over Q hot, only of the mysterious property of the reservoir, theta. Well, this is where we get to the next lesson. It's a postulate. Kelvin postulated that that mysterious characteristic is the temperature in absolute values, the temperature referred to absolute 0. But that will be the next lesson.